OSMOS software library for modeling and simulation of solar desalination systems. www.reslibrary.com.
Hi everybody, Professor Mohammed Sharaf with you. Let's talk about how to run reverse osmosis desalination plants by the using of REST software. First of all, we have to recognize what is the concept of, briefly, the concept of reverse osmosis. What is the possible configurations that should be run via REST library software, and how to run REST library for reverse osmosis, and how can we collect our data. First of all, the concept of reverse osmosis, briefly, it's some kind of water purification technology which uses semi-permeable membranes to remove ions, molecules, salins, solvents, and larger particles from drinking water to make it usable or suitable for human resources or human uses. First of all, it's quite applicable for drinking water, purification, some kind of military uses, food industry, hydrogen production, and so on. And reverse osmosis, the applied pressure is used to overcome the osmotic pressure itself by the using of high pressure pump effect that is driven by chemical potential and can give suitable potential differences of solvent and some kind of thermodynamic parameter related to the temperature of the feed lead to the high pressure pump. Reverse osmosis can remove many types of dissolved and suspended species from water, including bacteria, and is used for post-industrial processes and for production of potable water. The result simply is solute is retained on pressurized side of the membrane, and the pure solvent is allowed to pass to the other side, which, to be selective, this membrane should be not allowed large molecules or ions or some kind of such materials to go through the holes, but should allow smaller components, which is allowed of solution to pass freely through the membrane. This is the concept simply to produce such kind of fresh water. It can surely be used for seawater desalination, brackish water, and so on. Which configurations? Actually, there are many configurations for reverse osmosis, but we can categorize reverse osmosis into reverse osmosis with energy recovery devices and without energy recovery devices. The basic module is, of course, without energy recovery, and after that we have built-in energy recovery devices, this configuration, and pressure exchanger energy recovery device, which is currently widely used with reverse osmosis because it can reduce specific power consumption, plant costs, and running costs, and so on. This is the basic module. Feed water goes through the high pressure pump, and the high pressure pump increasing the pressure at maximum levels. If we are going to talk about large desalination plants, for example, 100 meter cube per hour, 500 meter cube per hour, 1000 meter cube per hour, we are going to talk about nearly 70 bars, 68 bars, 75 bars, up to 80 bars. So for this osmosis, we have the membrane mainly works on to divide the feed stream into two another streams, rejected streams, which is brine with salinity up to 50s, 60s, and so on, and permeate water, which is fresh water with low concentration salt that we are going to deal with. What is the cost of this inlet feed? What's the cost of the brine rejected? What's the cost of this? Is the analysis that we can handle based on the configuration, single stage, double stage, and so on. We have here, of course, this is the brine, as we saw from the past slide, that we have brine rejected. So with actually the pressure here is nearly the same as the pressure of the high pressure pump. So we have to utilize and harvest such a gain from this brine as much as we can. So the idea is to fix a built-in turbine in order to load sufficient power and can derive the high pressure pump, and the rest of the power can be used. Therefore, it can save or achieve more specific power consumption, lower specific power consumption, comparing against the first or the basic module. The third configuration is to use pressure exchanger unit, PEX device. This device is it's very impressive because its efficiency can be reached up to 98%, 99%, and so on. So it can exchange the pressure, and the pressure loss can be used for salt bonds and so on. And such pressure, without, we can say, we are going to overcome the obstacles and problems with split-to-wind drive, because it's turbo machinery device and so on. We have mechanical shaft efficiency, we have the split-to-wind efficiency, of course. We are talking about 70s, 85, 80%. So then the pressure device can transfer the pressure from the brine rejected into the splitted feed. We are going to here to use a splitter unit to split part of the feed, and such feed are going to use the pressure from the brine loss to be posted again and to the mixer unit, which can reduce a specific power consumption 1/3 from if we are going to compare against the basic module. Okay, how to run this model? Let's go and see how to run our model, how to select between such configurations. As you can see here, we have here, sure, if you are going to, you should specify your path after going to MATLAB. Specify your path from your opening to open your folder and download it. After you are going to download and something like that, we have to run this. It should be, the model should be appear like this one. Okay, double click on this, but be sure to specify or to assign from view model browser. You have to check this. You have to check these buttons to be sure that the model is fully appeared. Okay, double click on this. We have to assign some configuration. Let's go firstly with basic configuration. For basic configuration, we have to assign ambient temperature. Okay, this is ambient temperature. This is our reference temperature if we are going to deal with exergetic analysis and so on. And seawater temperature. Okay, seawater temperature, you can easily control it. Let it be 17. Yes, seawater salinity. Okay, but first we have after yes, seawater salinity. Consider it be 35,000 ppm, and the design reverse osmosis blend probability, I will choose 1,500 meter cube per day. Let's see the membranes. Selecting our membrane, I do recommend seawater with 30 high recovery with 380. Yes, area of membrane is 35. Okay. This is the number of pressure vessels. You are not allowed to go maximum than 8 pressure vessels, so we have to deal with maybe 7. It's fine. And the elements, I'm thinking of 35 elements per pressure vessel. Okay, let's see. Of course, for the performance, we have high pressure pump efficiency. Okay, it's suitable for 85. Fouling factor, it's okay. Recovery ratio, we can deal with okay, 30% is fine. Okay, for built-in device, you can assign the outlet turbine pressure, the turbine efficiency is 85, and the same for pressure exchanger unit, and this is the splitter ratio. Okay, it's 0.5. If we are going to run a pressure exchanger unit, this booster pump efficiency 85%. Pressure exchanger 98%, it's suitable and fine. And now let's go and run our model. Okay, let's see for the basic module. Okay, this is the first one. This is the basic module, built-in drive pressure exchanger configuration. Let's see here. Okay, now this is the element area, total element area. Specific power consumption is 4. The pressure is 42 bar. Okay, 42 bar. So we have to reduce the number of elements per pressure vessels. Let it be 40. No, 30. I'm sorry for this. Okay, it's 44. So this is the pressure. We need to increase the pressure a little bit. So let it be 20 elements. Apply. Okay, let's make another run. Yes, it's 50 bar and so on. So and surely specific work consumption is increased because it's cost, because you are going to increase the pressure. This is bumping power is 300 kilowatts, feed flow rate, brine flow rate, and brine salinity, distillate salinity or permeate salinity, product salinity, average salinity, specific entropy production, reversibility rate per kilowatt, feed exergy, brine exergy, and so on. Okay, so let's see if we are going to deal with another configuration, but dynamically. I mean, we're going to set the time limit for infinity, and let's hit our run. So we'll do this. make our run. Yes, let's see here. Okay, let's try to change the plant productivity and watch here what is going on here. Okay, the plant productivity is 1500. Okay, increasing. Yes, specific power consumption is increasing. Okay, increasing 2500, 3000, and this is a pressure. It reached to 68. Okay, okay. Let's increase the number of elements. Okay, using the pressure again. So you have to optimize. You can optimize your work, and so on. Okay, for going for larger productivities, for 5000, for example, here, as you can see here, 5000. As you can see here, raise it again. Number of elements again. Or we can reduce number of elements again to adjust it at 67. Yes, this we can handle this. Okay, so we can stop and we can make another run for filter wheel turbine. Let's see, filter wheel turbine. Wait, apply. Okay, go yes, for here. Let's see what is the specific bulk consumption. But first of all, we have to prepare this pen. Yes, hit run and watch the changes. Of course, the salinity. Let's check the salinity. Increasing the salinity rates, so specific bulk consumption will increase. Sure, if you are comparing with the basic one, filter wheel will compete well because it's energy recovery device. But increasing the salinity up to higher rates will consume more power, as you can see here, up to 40, 45. Okay, let's go for 45,000 ppm and increasing the elements up to 42, 60. Yes, that's quite normal if we compare against the other. And so on, you can watch here. You can see here, this is filter wheel power. This is the power provided by the filter wheel. It can provide us with 700 kilowatts. Okay, 700 kilowatt. You have to subtract from the high pressure pump, so we are going to save much power. 1500. You can subtract it almost as a half, almost. Okay, let's stop and let's run some analysis. Going with some analysis. Yes, for the first run. Okay, the second. Yes, this is our runs. We can draw some figures related to a specific power consumption. Okay, this is a specific power consumption. I think this one. Okay, for the specific power consumption, we can here watch the effect of increasing or decreasing the salinity, the number of elements per pressure vessel, the energy, the recovery ratio of the reverse osmosis plant. And we can see here, this is, of course, sure, this for irreversibility. is exergy destruction rate, and this is exergetic feed, exergy of the brine, as we can see here. Okay, for this we can discover the power of the high pressure pump. Okay, and here we can discover the salinity of the brine, the average salinity, and so on. So we can also discover this is the delta B, pressure difference across the pump, as you can see here, fluctuating according to your inputs. Seawater, we have many analysis to address and to deal with. We have a lot of analysis to optimize and to discover what is the best effect on the module. Is it for regarding to the salinity, regarding to the seawater temperature, or the plant productivity at the same area, or sure. Number of elements, effect, what is the recovery ratio effect on the plant, and so on. So we have a lot of parameters to adjust and to discover what is the best effect on our module, and so on. This is sure we have to select here from the beginning. Pressure exchanger, your energy recovery. Let's go for 3500, salinity 45, and the same area. Pressure, I think it's 40 elements. It's quite good. Recovery ratio 35, and splitter ratio, I think it's 70% is fine, and the rest is good. Let's see. Let's watch the specific pump consumption. Let's go with yes, as you can see here, the specific bulk consumption, the pressure, mass flow rate of the brine, of the feed, and so on. The same data you can collect. This is a booster pump unit. You can collect the booster pump power, flow rate to the mixer, flow rate salinity to the mixer unit, and this is the pressure from the pressure exchanger unit of the brine, pressure of the brine, salinity stream to the booster pump, feed to the booster pump, and so on. You can discover a lot of useful data to deal with. Okay, finally, we are going to say we have a dynamic model. We can discover and to examine out of the effect of many parameters on the reverse osmosis performance, and we can collect our design data and so on. Don't forget to download your reverse osmosis sensor plant with power cycle, thermal power cycle, or electric power cycle, with geothermal plant, with a solar Rankine cycle, photovoltaic with vertical wind turbine unit, a fuel cell with powering reverse osmosis, and so on, and a lot of many. Thank you for watching. Follow us at redcelebrator.com, YouTube channel, Facebook, subscribe and like. Thank you very much.